Now I want to talk about the greenhouse effect, because the greenhouse effect is a very important process on Earth that actually keeps the Earth's average temperature about 30 degrees warmer than it would be otherwise if we did not have it. So the greenhouse effect kind of has a little bit of an iffy wrap to it, simply because we talk about greenhouse gases a lot and we associate that with man-made climate change. However, the greenhouse effect and greenhouse gases in general are a very important thing, because the Earth would be about 30 degrees cooler if we did not have the greenhouse effect. So what is the greenhouse effect? Well, simply put, an atmospheric less body, what actually does heat transfer look like? And so out of all the energy that the sun gets, if a planet or our planet didn't have any kind of greenhouse gas, all that incoming radiation would be re-radiated back out into space. So incoming solar radiation, what's known as shortwave radiation, all of that incoming amount is therefore lost to space when the sun goes down. And this is what's known as long wave radiation. So short wave radiation comes in and long wave radiation comes out. This would be like you working a job, and let's say you made $100 in your paycheck and you give that $100 right back to your employer. Now, what kind of job would that be? Exactly. So when we look for a planet like ours that has a modest amount of greenhouse gases, we know that, yes, out of all the incoming shortwave solar radiation, we do have long-wave radiation that does go back out to space, but we do have some long-wave radiation that actually gets re-radiated back down to the surface of the Earth, and that's because of our greenhouse gases. So if you think about it, right, we have all of the incoming solar radiation. So let's take our paycheck example. So let's say that we made $100 in our paycheck this week, and let's say 50% went back to the employer, or went to taxes or health insurance, or let's say 50% went to bills in general, and then the other 50% you actually got to keep or to take home. So that is an example of how the greenhouse gases work. Now there's three main greenhouse gases on the planet Earth. The most abundant and the most important is water vapor. Water vapor plays a huge role in regulating the Earth's temperature. The second most abundant greenhouse gas would be carbon dioxide. Now you've heard of this many of times, especially when we talk about climate change. Carbon dioxide always gets a bad rap, but carbon dioxide in the right amount is actually good, and it's a great greenhouse gas. The third greenhouse gas, and the most effective greenhouse gas, is methane. Methane is 3 times as effective as a greenhouse gas than carbon dioxide, but you don't hear about methane as much just because our byproduct or our waste from energy is not in the form of methane, but it's in the form of carbon dioxide. So that's the whole bad rap that you hear when we talk about man-made climate change. However, all three greenhouse gases are very important because they help keep the atmosphere or the Earth about 30 degrees warmer than what it would be. So this would be like saying a typical summer day is 50 degrees if we didn't have greenhouse gases. Well, we know that a typical summer day can easily be 80 degrees. So imagine a typical summer day being 50 degrees. It doesn't seem that nice. So now you see how greenhouse gases are actually a really good thing. So this is the process that happens here on Earth. Now, in an extreme event, if this was like the planet Venus, all incoming shortwave radiation can't really escape the surface of Venus because of the thick clouds that are not made up of water vapor, but they're made up of carbon dioxide. That carbon dioxide is in great abundance on the planet Venus. And so those carbon dioxide clouds, they're very, very thick, and they prevent any long wave radiation from escaping Venus. So any kind of long wave radiation that escapes from Venus is absorbed by those clouds and then re-radiated back down to the surface of the Earth. So in our employer example, this is like saying you get $100 in your paycheck this week and you keep the $100. And then next week you get another $100 in your paycheck and you keep the next $100, and so on and so forth. So that's why Venus is very warm. other than the fact that it's the second planet from the sun and gets more solar energy, it's also due to the greater abundance of greenhouse gases. So when we actually look at it in retrospect, this is how the Earth's greenhouse effect works compared to Venus's greenhouse effect. So yes, when the sun is out, the temperature is the warmest here on Earth. And at nighttime, temperature cools off because the sun is down and some of that long wave radiation is actually able to escape back out into space. But not all of it escapes back out into space. Here you can see in this diagram that some of that long wave radiation gets absorbed by the clouds in the atmosphere and then is re-radiated back down to the surface. So this is what keeps the surface of the Earth about 30 degrees warmer than it would be if we didn't have that effect. Now, on the contrary, Venus, right, all of that incoming solar radiation, any long wave radiation that tries to escape Venus's atmosphere actually just gets reabsorbed by the thick carbon dioxide clouds and gets re-emitted back towards the surface. In a real world example, here's 3 different scenarios that happen at night, and you're going to find this very useful for when you actually create your own weather forecasts. So let's take 3 examples, and let's say that we have a clear night, a partly cloudy night, and a overcast night. So at night, there's no clouds here on the clear night on the left-hand side. So this means that temperature can cool off drastically when there's no clouds. It makes sense because there's no cap, there's no blanket in order to keep the Earth warm. Clouds act as a blanket, keeping the Earth warm. So all of that solar energy that was received throughout the course of the day now escapes back out into space, and the temperature at night can drop off rather drastically. Now, if we have some clouds around, you notice that the temperature doesn't escape, or the radiation doesn't escape fully to the atmosphere. Some of it is absorbed by the clouds and then re-radiated back down to the surface of the Earth. But on an overcast night, we notice that the temperature swing doesn't necessarily move all that much because all the long wave radiation trying to escape from the Earth's atmosphere actually gets absorbed by the clouds and then re-radiated back down to the surface, keeping our atmosphere warm. So on a cloudy night, if you've ever noticed, especially if you wake up early in the morning, if it's been a cloudy night, you walk outside, sometimes it's not as cold out than it would be, or than it would have been on a totally clear night. So when we look at the Earth as a whole, we have to look at the Earth's total heat energy budget. And if we ignore climate change, we ignore all that, what is the Earth getting warmer or colder? And the answer is neither. The Earth is in a good spot. The Earth is not getting warmer and it's not getting colder. And so it is actually in balance. But we do notice that most of our heat is absorbed between about 25 degrees both north and south latitude and the equator. So we know that the subtropics and the tropics, where it's the warmest, they receive most of the sun's solar energy, whereas the poles will lose most of that energy. So this means that between the poles and the equator, heat energy balance is actually in balance. So the Earth is not getting warmer or it's not getting colder.